Hello, everyone. I'm Yazan Ibrahim, or as some of you might know me, Yazan Abu Ghosh. Today, we're going to dive into a fascinating and essential topic. Welcome, everyone, to a fascinating journey into the hidden world of artificial intelligence, a world that doesn't always involve flashy tech demos or sci fi robots, but rather the complex systems, trusted professionals, and intricate decisions shaping our future. Today, we're not diving into shadowy alleys, but into sleek boardrooms and the quiet clicks of data centers where AI's power is harnessed. This isn't just about algorithms or quick efficiencies, it's about understanding how trust, risk, and accountability intertwine in this new technological era. And that brings us to the heart of today's discussion, the new ISACA credential, Advanced in AI Auditing Team, AAIA. This isn't just another certification, it's a validator of your ability to audit the complex systems that AI creates and to mitigate the unique risks that come with it. In a world where AI can be a powerful tool for good but also a source of hidden vulnerabilities, the AAIA equips professionals like you to be the guardians of integrity and security. To truly grasp the significance of the AAIA and how to audit AI effectively, we first need to build a strong foundation. That's why our initial focus will be on Chapter 1, AI models, considerations, and requirements. This chapter introduces the fundamental building blocks and conceptual underpinnings of AI, which are essential for anyone involved in AI governance, operations, or auditing. We'll cover the various forms AI can take, the models and algorithms that power it, its life cycle, and overarching business implications. So grab a seat, maybe a cup of coffee, and let's unravel what this cutting edge credential is all about over the next 40 minutes. By the end of our session, you'll not only understand the AAIA certification, its requirements, domains, and benefits, but also see how it positions you to navigate the complexities of AI, ensuring it's used responsibly and ethically. Let's explore how you can become a leader in this critical field. Stay curious and let's dive in. All right, let's begin with the very basics, the bedrock of our understanding. Section 1.1, Types of AI. Now, when we say types of AI, it's not as simple as sorting apples and oranges. It's a rich tapestry, a multi layered landscape. Think of it like biology. You have kingdoms, phyla, classes, orders, all different ways to categorize and understand living things. AI is similar. We need to appreciate it not as one single thing, but through its various dimensions. This means looking at its core concepts, the common acronyms you'll hear bandied about, its distinguishing characteristics, the different ways it learns, its inherent capabilities, its cognitive abilities, and very importantly, how it's being classified by regulatory bodies like the EU AI Act based on risk. So let's unpack some of these key concepts and types of AI. First up, the term that started it all, artificial intelligence, AI itself. At its heart, AI is the theory and the ongoing development of computer systems that can perform tasks that typically require human intelligence. This could be anything from understanding language to recognizing faces, making decisions, or solving complex problems. It's about creating intelligence, not just programming instructions. Next, we have machine learning and ML. This is a crucial subset of AI. Instead of explicitly programming a computer for every single scenario, machine learning is about enabling a model to learn from data. It's the process of optimizing a model's parameters using computational techniques so the model's behavior reflects the data or experience it's been fed. It's like teaching a child by showing them examples rather than writing out an exhaustive rule book for every possible situation. Then there's knowledge. In the context of AI, knowledge refers to the structured information that these systems use to make decisions and solve problems. It's what enables automated reasoning. Think of it as the curated library an AI system consults to act intelligently. And of course, neural networks. You've likely heard this term. Imagine a vast interconnected web inspired by the structure of the human brain. A neural network consists of one or more layers of neurons, computational units, connected by adjustable weighted links. It takes input data, processes it through these layers, and produces an output. These are incredibly powerful for tasks like image recognition or complex pattern detection. Now let's decode some common concepts and acronyms on AI systems that you'll encounter frequently. First, AGI, which stands for Artificial General Intelligence. This is the kind of AI often depicted in science fiction, systems with human like cognitive abilities across a wide variety of domains. An AGI wouldn't just be good at playing chess, it could also write poetry, understand emotions, and learn entirely new skills, much like a human. We're not quite there yet, but it's a significant area of research and aspiration. Then there's ASI, or artificial superintelligence. This is a hypothetical form of AI that would surpass human intelligence in virtually all fields, intellectually, creatively, socially. It's a concept that brings with it immense possibilities and profound ethical questions. We've already touched on ML, or machine learning, which, as a reminder, is that subset of AI focused on algorithms that learn from data. It's the engine behind many of the AI applications we see today. NLP stands for natural language processing. This fascinating branch of AI deals with the interaction between computers and human language. It's about enabling machines to understand, interpret, and generate human language. Think of chatbots, translation services, or sentiment analysis tools. CV, or computer vision, is another exciting area. This field of AI is focused on enabling computers to interpret and understand visual information from the world around them, like images and videos. Self-driving cars heavily rely on computer vision, as do facial recognition systems and medical image analysis tools. And finally, in this group of acronyms, we have RL, which stands for reinforcement learning. This is a type of machine learning where an AI agent learns to make a sequence of decisions by trying them out and learning from the consequences, essentially learning through trial and error, receiving rewards for good actions and penalties for bad ones within a dynamic environment. Imagine training a dog with treats. That's a simple analogy for reinforcement learning. Let's now explore some fundamental types and characteristics of artificial intelligence. We often talk about an AI agent. What is it? An AI agent is an automated entity that can perceive its environment through sensors and act upon that environment through actuators, all in pursuit of achieving its objectives. A self-driving car is an agent, a smart thermostat can be considered an agent, even a sophisticated software bot playing a video game. Then we have a conceptual distinction, symbolic AI. This is often referred to as good old-fashioned AI or GOFAI. Symbolic AI is based on techniques and models that manipulate symbols like words or logical predicates and structures according to explicitly defined rules and logic to derive inferences. Think of expert systems that try to codify the knowledge of a human expert into a set of rules. Contrasting with that is subsymbolic AE. This approach is quite different. Subsymbolic AI is based on techniques and models that use an implicit encoding of information, which is typically derived from experience or raw data rather than explicit rules. Neural networks are a prime example of subsymbolic AI. The knowledge is embedded in the weights and structure of the network, learned from data, not programmed as a list of if-then statements. Now let's delve a bit deeper into the approaches to machine learning, as these are critical to understanding how AI models are built and trained. First, supervised learning. This is perhaps the most common type. In supervised learning, the machine learning model is trained on labeled data. This means the training data includes both the input and the desired output. It's like teaching a student with a textbook that has questions and the corresponding answers. The model learns to map inputs to outputs based on these examples. Spam detection is a classic example. Emails are labeled as spam or not spam, and the model learns to identify new spam emails. Next is semi-supervised learning. As the name suggests, this approach sits between supervised and unsupervised learning. It uses a combination of both labeled and unlabeled data during training. Often there's a small amount of labeled data and a large amount of unlabeled data. This is useful when labeling data is expensive or time-consuming. The model tries to leverage the structure in the unlabeled data to improve its learning from the labeled data. Then we have unsupervised learning. In this case, the machine learning model is given only unlabeled data during training. The goal is to find hidden patterns, structures, or relationships within the data itself without any predefined outputs. Think of it like giving someone a pile of unsorted photos and asking them to group the similar ones. Clustering customers into different segments based on their purchasing behavior is an example of unsupervised learning. And we've mentioned it before, but it's a distinct approach, reinforcement learning. Here, the AI agent learns by interacting with an environment. It learns an optimal sequence of actions to maximize a cumulative reward through trial and error. This is very powerful for teaching AI to play games, control robots, or optimize complex processes where the right answer isn't known upfront, but good outcomes can be rewarded. AI can also be categorized based on its capabilities. We often hear about narrow AI, sometimes called weak AI. This type of AI is specialized in performing a specific task or a narrow range of tasks. All the AI we currently use in our daily lives falls into this category, from virtual assistants like Siri or Alexa to recommendation systems on Netflix or AI that can play chess at a grandmaster level. They are brilliant at their specific job, but can't operate outside that defined scope. The next step up conceptually is general AI, or artificial general intelligence, AGI, which we mentioned earlier. This is AI that possesses the ability to understand, learn, and apply knowledge across a wide range of tasks, much like a human being. It could switch from translating languages to solving mathematical problems to composing music with a level of adaptability and general cognitive function similar to ours. This is still largely theoretical, and beyond that is strong AI. This term is sometimes used interchangeably with AGI, but it can also refer to AI that has cognitive capabilities similar to or even superior to those of humans, potentially including consciousness or self awareness. This too is a future concept. This brings us to classifying types of AI systems based on cognitive capabilities, which offers another lens. First, reactive machines. These are the most basic types of AI systems. They can react to current stimuli based on pre programmed rules, but they cannot form memories or use past experiences to inform current decisions. IBM's Deep Blue, the chess playing computer that beat Garry Kasparov, was a reactive machine. It could analyze the current board and choose the best move, but it didn't remember past games in the way a human does. Next are systems with limited memory. Most AI systems in use today fall into this category. They can look into the past to a certain extent and use that historical information to make better decisions in the short term. For example, self driving cars use sensor data from the recent past, like the speed and direction of nearby cars, to navigate. The memory isn't stored permanently like human long term memory, but it's used for the immediate decision making process. Then we have a more theoretical category, theory of mind AI. This refers to AI that would be capable of understanding human thoughts, emotions, beliefs, and intentions, essentially having a theory of mind similar to what humans develop. Such AI could interact with us in much more nuanced and socially intelligent ways. This is a major area of research, but not yet a reality. And finally, the most advanced hypothetical stage, self-aware AI. This type of AI would possess self-awareness, consciousness, and the ability to reflect on its own existence and internal states. It's the stuff of deep philosophical debate and science fiction, far beyond our current technological capabilities. Lastly, in this section on types of AI, it's crucial to understand the classification of AI systems according to the EU AI Act. As AI becomes more pervasive, regulations are emerging, and the EU AI Act is a landmark piece of legislation that classifies AI systems based on the risk they pose. This is incredibly important for anyone involved in AI governance and auditing. The EU AI Act defines several risk categories. Minimal or no risk. These AI systems pose little to no threat to citizens' rights or safety. Examples might include spam filters or AI in video games. For these systems, there are no specific legal requirements under the Act, though voluntary codes of conduct are encouraged. Limited risk. These AI systems have specific transparency obligations. For example, when you're interacting with a chatbot, it should be made clear that you're communicating with an AI, not a human. This helps users make informed decisions. High risk. This is a critical category. AI systems classified as high risk are subject to strict requirements before they can be put on the market and throughout their life cycle. This includes things like robust risk management systems, high quality data sets, detailed documentation, human oversight, and high levels of accuracy and security. Examples include AI used in critical infrastructure like transport, medical devices, recruitment, law enforcement, or credit scoring. The AAIA credential will be particularly relevant for auditing systems in this category. Unacceptable risk. These are AI systems that are deemed to pose a clear threat to the fundamental rights and safety of people. Such systems are prohibited in the EU. Examples include AI systems that manipulate human behavior to circumvent users' free will, like toys using voice assistants to encourage dangerous behavior in minors, systems that enable social scoring by public authorities, and certain types of remote biometric identification systems in public spaces used for law enforcement, with some narrow exceptions. Understanding these classifications is vital because they dictate the legal and compliance obligations that AI systems must meet, and therefore what auditors will need to verify. Now that we have a better grasp of the different types of AI, let's move on to section 1.2, machine learning AI models. These models are truly the engine room of most modern AI systems. And it's not just about the models themselves. The interaction and collaboration between humans and AI are absolutely central to how AI solutions are designed, implemented, and how their value is ultimately realized. We've already discussed the main machine learning approaches, so let's quickly recap them as they form the basis of these models. Supervised learning, learning with labeled data, like having an answer key. Semi-supervised learning, a mix of labeled and unlabeled data making the most of what's available. Unsupervised learning, discovering patterns in unlabeled data like finding natural groupings. Reinforcement learning, learning through trial and error guided by rewards and penalties. These approaches are the methodologies used to train the AI models. But how do these models then work with humans? This is where models of human AI cooperation come into play. Several frameworks help us understand and design this crucial interaction. First, consider the Deloitte Augmented Intelligence Framework. This framework views AI in terms of how it interacts with human capabilities. AI can automate, taking over repetitive tasks previously done by humans, augment, enhancing human capabilities, helping people do their jobs better or faster, amplify, scaling human expertise, allowing a few experts to have a much broader impact. It's about AI as a partner, not just a replacement. Next, there's the PwC AI augmentation spectrum. This model categorizes AI's role based on two dimensions: the autonomy of the AI system and the role complexity it handles. It identifies several roles for AI, such as executor, AI performs well-defined tasks; self-learner, AI improves its performance over time based on new data; assistant, AI provides support and information to humans; co-creator, AI works alongside humans in creative or problem-solving tasks; decision maker, AI makes certain decisions autonomously with human oversight; advisor, AI provides recommendations and insights to guide human decisions. This spectrum helps organizations think about the different ways AI can be integrated into workflows. Then we have the MIT Human in the Loop, HITL AI model. This is a very practical and widely adopted model, especially in systems where accuracy and safety are paramount. The typical flow involves AI suggestion. The AI model makes a prediction or suggests an action. Human review. A human expert reviews the AI suggestion. This is critical for catching errors, handling edge cases the AI might not be trained for, or applying contextual judgment. AI adaptation, the feedback from the human review confirming or correcting the AI, is then used to further train and improve the AI model over time. This creates a virtuous cycle of continuous improvement. Another valuable framework is the Harvard Human AI Teaming Model. This model looks at the relationship between humans and AI as a form of teaming, identifying different roles the AI can play within that team. AI as a tool. Here, AI provides specific functionalities that humans control directly, much like using a sophisticated calculator or a search engine. AI as a collaborator. In this mode, AI works more like a partner, contributing unique capabilities to a shared goal. For example, an AI might analyze vast data sets to identify patterns that a human researcher then explores further. AI as a manager. In some scenarios, AI might take on a coordinating or managerial role, perhaps by assigning tasks to humans or other AI systems, or by optimizing workflows. This requires a high degree of trust and sophistication. Finally, let's look at the Microsoft AI maturity models. Microsoft offers a couple of models that help organizations assess their journey with AI. Model 1, Progression to Autonomy. This model describes a progression. Assisted intelligence. AI helps humans perform tasks more efficiently, e.g., grammar checkers. Augmented intelligence. AI enhances human decision-making by providing insights or automating parts of a task, such as diagnostic support for doctors. Autonomous intelligence. AI systems operate independently to achieve goals with minimal human intervention in specific, well-defined contexts, which are autonomous robotic vacuum cleaners. Model 2, the organizational AI adoption stages. This model looks at how organizations adopt AI. Foundational, the organization is just starting to explore AI, perhaps with pilot projects. Approaching, AI initiatives are becoming more common, with some successes and established practices. Aspirational, the organization has a clear vision for AI and is strategically investing in it. Mature, AI is deeply integrated into the organization's strategy and operations, driving significant value. These models of human AI cooperation are not just theoretical, they guide how AI systems are designed, what level of human oversight is needed, and how organizations can best leverage AI to achieve their goals. For an AI auditor, understanding these frameworks is key to assessing whether the human AI interaction is designed appropriately for the risks involved and the objectives of the system. Having explored AI models and how humans interact with them, let's now turn our attention to the very core of how these models learn and operate. Section 1.3, Algorithms. Algorithms are the recipes, the set of instructions that make AI, and particularly machine learning, work. The choice of algorithm is a pivotal decision made during the design and development phase of an AI system and is influenced by a range of factors like the desired accuracy, how interpretable the model needs to be, and its computational efficiency. Let's first clarify their role in machine learning and AI models. As we know, machine learning is about optimizing a model's parameters using computational techniques, and those techniques are algorithms so that the model's behavior reflects the data or experience it has been shown. When an AI model is designed, this encompasses its structure, the algorithms it will use for learning and inference, and the processing mechanisms that will bring it to life. All of this must be aligned with the business objectives and critically with ethical guidelines. The algorithm is the specific mathematical procedure that enables the learning process. A particularly important application of algorithms is within algorithms in neural networks. Neural networks, with their brain-inspired architecture, rely on sophisticated algorithms for training. Two of the most foundational are backpropagation. Imagine a message passing forward through the network to make a prediction, and then an error signal passing backward through the network to adjust the connections, the weights, to reduce that error. That's essentially backpropagation. It's an algorithm that efficiently calculates how much each weight in the network contributed to the error, so those weights can be tweaked in the right direction. Gradient descent. This is an optimization algorithm often used with backpropagation. Think of trying to find the lowest point in a valley while blindfolded. You'd feel around for the steepest slope downwards and take a step in that direction. Gradient descent does something similar mathematically. It iteratively adjusts the model's parameters, the weights in a neural network, to minimize a loss function which measures how wrong the model's predictions are. Neural networks also use activation functions. These are crucial components within each neuron. They introduce non-linearity into the network. Why is this important? Most real-world data and problems are complex and non-linear. Without activation functions, a neural network, no matter how many layers it has, would behave like a simple linear model, severely limiting its ability to learn complex relationships in the data. So these functions decide whether a neuron should be activated or not, adding the necessary complexity. The approaches to machine learning that we've discussed, supervised, semi-supervised, unsupervised, and reinforcement learning, each have their own families of algorithms associated with them. Supervised learning algorithms include things like linear regression, logistic regression, support vector machines, decision trees, and of course, many types of neural networks. Semi-supervised learning often involves adapting supervised algorithms or using techniques like generative models or graph-based methods. Unsupervised learning uses algorithms like k-means clustering, hierarchical clustering, principal component analysis, PCA, and autoencoders. Reinforcement learning relies on algorithms such as Q-learning, SARSA, and deep Q networks, which combine Q-learning with deep neural networks. The choice from these categories and specific algorithms within them is a fundamental design decision. This leads us directly to algorithm selection in AI system development. This is a critical step that occurs during the design and development phase of the AI lifecycle. When developers are building an AI system, they must choose the most appropriate AI models and the specific algorithms that will power them. This decision isn't arbitrary, it's based on several factors. Accuracy. How well does the algorithm perform on the given task? This is often measured by specific metrics relevant to the problem, e.g., precision, recall, F1 score. Interpretability or explainability. How easy is it to understand why the model makes the decisions it does? For some applications, like medical diagnosis or loan applications, high interpretability is crucial for trust, debugging, and regulatory compliance. Some algorithms, like decision trees, are inherently more interpretable than others, like complex, deep neural networks, which are often called black boxes. Computational efficiency. How much computing power and time does the algorithm require to train and to make predictions? This can impact the cost and feasibility of deploying the AI system, especially for real-time applications or models that need to be retrained frequently. Data requirements. Some algorithms need vast amounts of data, while others can perform reasonably well with smaller data sets. The nature of the available data, e.g., labeled or unlabeled, volume, variety, also influences algorithm choice. Scalability. Can the algorithm handle growing amounts of data and increasing complexity as the system evolves? The selection process often involves experimentation, trying out several algorithms and tuning their parameters to find the best fit for the specific problem and its constraints. For an AI auditor, understanding the rationale behind algorithm selection is key to assessing whether the chosen methods are appropriate, robust, and aligned with the system's intended use and risk profile. So we've talked about types of AI models and the algorithms that drive them, but how do these pieces come together in a structured way? That's where section 1.4 AI lifecycle comes in. The AI lifecycle, often referred to as the AI Systems Development Lifecycle, AI SDLC, describes the various stages involved in planning, creating, testing, and deploying AI systems. It's crucial to understand that the AI SDLC has some unique characteristics. It emphasizes data as a core component, it has model-centric stages, and it requires integrated ethical oversight throughout. It's generally more iterative and data-focused than many traditional software development life cycles. Imagine a circular or iterative flow, because AI systems are rarely finished. They evolve. The AI system lifecycle diagram generally looks something like this, with feedback loops connecting many stages. Requirements and specifications. This is where it all begins. Then arrows leading downwards or iteratively to design and development, data planning, collection and preparation, model training and evaluation, verification and validation, deployment, operations and monitoring, with arrows indicating this can feed back into earlier stages for retraining or redesign. And running alongside or underpinning all these stages, technical documentation, an ongoing process, recording of events, also ongoing, and as cross-cutting concerns that apply throughout the entire life cycle, ethical oversight, AI resources, and defined criteria and requirements. Let's walk through each of these key stages in the AI system lifecycle. The first, requirements and specifications. This initial phase is about clearly defining the AI system's purpose. What problem is it trying to solve? What are the goals and specific use cases? This stage also involves defining ethical and compliance standards from the outset, conducting initial risk and impact assessments, and establishing the performance metrics that will be used to judge the system's success. Without clear requirements, the project is likely to drift. Second, design and development. Once the requirements are clear, the team moves to create the actual model structure, choose the algorithms as we just discussed, and design the processing mechanisms. Key activities here include selecting appropriate algorithms based on factors like accuracy and interpretability, specifying the data requirements for training and operation, consciously integrating fairness considerations to mitigate bias, implementing security by design principles, defining the mechanisms for human oversight, especially for high-risk systems, and ensuring the AI system can be integrated with other existing systems or workflows. Third is data planning, collection, and preparation. Data is the lifeblood of most AI systems, especially machine learning models. This stage is absolutely critical. It involves defining strategies for data acquisition. Where will the data come from? Data storage, how will it be securely managed? And data governance, who owns it, who can access it, how is quality ensured? The actual work involves gathering the necessary data, cleaning it, which can be a huge task, dealing with missing values, errors, inconsistencies, structuring it appropriately, and often labeling it if supervised learning is being used. The quality of the data directly impacts the quality of the AI model. Garbage in, garbage out, as they say. Fourth, model training and evaluation. With prepared data in hand, this is where the machine learning models are actually trained. The chosen algorithms are applied to the training data, and the model learns to identify patterns or make predictions. After the initial training, the model's performance is rigorously assessed against predefined metrics for accuracy, fairness, checking for biases against certain groups, and ethical compliance. This stage often involves splitting the data into training, validation, and test sets to ensure the model generalizes well to new unseen data and isn't just memorizing the training examples. Fifth, verification and validation, V&V. This is a crucial checkpoint. Verification asks, are we building the system right? It ensures the AI system functions as intended according to its design specifications. Validation asks, are we building the right system? It confirms that the system actually meets the user needs and requirements defined in the first stage. V&V processes assess accuracy, reliability, compliance with legal and ethical standards, explainability, can we understand its decisions, and robustness, can it handle noisy or unexpected inputs. Sixth, deployment. Once the model has been trained, evaluated, and validated, it's ready to be implemented in a real-world or production environment. Deployment isn't just flicking a switch, it needs to be carefully planned. This might involve a phased rollout, starting with a controlled environment or a pilot group before a full-scale launch. Seventh, operations and monitoring. An AI system is not a deploy and forget technology. Once live, it requires continuous monitoring. This involves tracking its performance in real time, detecting any degradation in accuracy, a concept known as model drift, where the model becomes less accurate over time as the real world data changes, identifying new risks or compliance gaps, and watching for any deviations from expected behavior. This monitoring often triggers retraining or updates to the model. Eighth, technical documentation. This isn't a single stage, but an ongoing activity throughout the entire life cycle. It involves maintaining detailed records of the AI system's design, the decisions made, e.g., why certain algorithms or data sources were chosen, development processes, training procedures, evaluation results, and any updates or changes. Good documentation is essential for transparency, accountability, maintainability, and for auditing purposes. Ninth, recording of events. Similar to technical documentation, this is an ongoing process. It means logging important incidents related to the AI system, the key decisions made by the AI, especially in autonomous systems, and any significant operational impacts. This audit trail is vital for accountability, for investigating issues, and for demonstrating compliance. Now, let's look at the cross-cutting considerations that permeate every stage of the AI lifecycle. Ethical oversight. This cannot be an afterthought. Ethical principles like fairness, non-discrimination, transparency, accountability must be integrated into every phase, from requirements, definition, and data collection through model development and deployment to ongoing monitoring. This might involve ethics committees, impact assessments, and specific design choices to promote ethical outcomes. AI resources. Developing and maintaining AI systems requires significant resources. It's important to document the necessary human expertise, data scientists, AI engineers, domain experts, ethicists, the computational infrastructure, hardware, cloud services, data sources and their management, software tools and platforms, and the financial investments required at each stage. Criteria and requirements. Throughout the life cycle, there needs to be a clear definition of criteria, requirements, and processes for each stage. What are the exit criteria for moving from design to development? What are the quality thresholds for data? What are the performance benchmarks the model must meet before deployment? These provide a framework for governance and quality assurance. Understanding this AI lifecycle is fundamental for an AI auditor. It provides the roadmap for examining how an AI system was built, how it operates, and whether appropriate controls and considerations were applied at each step. We've laid a lot of groundwork on the technical aspects of AI. Now, let's shift our focus to why organizations are so interested in AI and the critical factors they must consider from a business perspective. This brings us to section 1.5, business considerations. AI presents a fascinating duality. It offers truly significant opportunities and strategic advantages, but it also introduces substantial business risks. Therefore, a balanced approach, underpinned by robust governance and meticulous risk management, is absolutely essential. Organizational preparedness isn't just helpful, it's critical for success. Let's start with the exciting part: business opportunities and strategic advantages that AI can unlock. Increased value. This is a broad category, but AI can create value in numerous ways. It can lead to significant productivity gains by automating tasks. It can drive cost savings by optimizing processes or reducing errors. AI enables deep personalization of products and services, enhancing customer satisfaction. It can help businesses develop entirely new services or business models that weren't previously possible. It allows organizations to unlock the insights hidden within their data, turning it from a passive asset into a strategic driver. And it can dramatically improve decision making by providing more accurate, timely, and comprehensive information. Competitive edge. In today's fast-paced market, AI can be a powerful differentiator. Organizations that effectively leverage AI can achieve market leadership by offering superior products, more efficient services, or entirely new value propositions. AI can create a significant differentiation from competitors who are slower to adopt. Operational efficiency. This is often one of the first areas where businesses see AI benefits. AI can streamline complex workflows, automate repetitive manual processes, and enable greater organizational agility to respond to changing market conditions or customer demands. Stakeholder trust. While AI also poses risks to trust, which we'll discuss, when AI is developed and deployed transparently and ethically, it can actually build stakeholder trust. Showing that AI is being used responsibly can enhance a company's reputation with customers, employees, investors, and regulators. We also see specific use cases across various business functions. In security, AI is revolutionizing areas like fraud detection, anomaly detection in network traffic, and threat intelligence. In operations, AI powers predictive maintenance, fixing machines before they break, supply chain optimization, and quality control. In customer experience, AI enables personalized recommendations, 24/7 customer support through chatbots, and sentiment analysis to understand customer feedback at scale. In business processes, AI is used for automation of tasks like data entry, document processing, and even aspects of HR and finance. To seize these opportunities effectively, organizations need robust AI strategy and planning. This starts with AI strategy design. It's not about doing AI for AI's sake. The AI strategy must be tightly aligned with the overall business strategic objectives. It involves identifying high impact use cases where AI can solve real problems or create significant value. What are the key business goals and how can AI help achieve them? This leads to the development of strategic roadmaps. These roadmaps outline the path for AI adoption and can vary in focus. Some organizations might initially focus on managing risks and adopting AI defensively to keep up with compliance or basic industry standards. Others might pursue defensive adoption to maintain parity with competitors. And more ambitious organizations will aim for competitive advantage, using AI to innovate and lead their market. When developing these strategies, there are key strategic considerations. A useful mnemonic here is policy. What internal policies are needed for AI development, deployment, ethics, and data governance? Process. How do existing business processes need to change to incorporate AI? What new processes are needed for the AI lifecycle itself? People. What skills and talent are required? How will the workforce be trained or upskilled? What is the impact on company culture? Physical infrastructure. What are the hardware and networking requirements? Information. This refers to the data, its availability, quality, governance, and security. Technology. What AI platforms, tools, and technologies will be used? Addressing each of these dimensions is crucial for a comprehensive AI strategy. Part of this strategic planning is conducting an organizational AI readiness assessment. Before diving headfirst into large-scale AI projects, it's wise to evaluate how prepared the organization truly is. This involves looking at internal contexts. Is the AI strategy aligned with the overall business strategy? Is there strong leadership commitment and sponsorship? Are relevant policies and governance structures in place? What is the state of the organization's data maturity and infrastructure? Are the necessary skills available, or is there a plan to acquire them? Is there a strong ethical framework? And of course, is there an adequate budget allocated? External contexts. What are the prevailing market trends in AI adoption within the industry? What are competitors doing with AI? What are customer expectations regarding AI-enabled products or services? And critically, what are the relevant legal, regulatory, and ethical factors in the external environment? To help with this assessment and strategic planning, organizations can use well-known analytical tools such as Pestel analysis. This framework helps analyze the political, economic, social, technological, environmental, and legal factors in the macro environment that could impact the AI strategy. SWOT analysis. This classic tool helps identify the organization's internal strengths and weaknesses related to AI and the external opportunities and threats. Now, let's turn to the other side of the coin. AI-related business risks. While the opportunities are vast, the risks can be equally significant if not managed properly. Competitive risk. This is the risk of falling behind. Failure to adopt AI where competitors are doing so effectively can lead to loss of market share, reduced efficiency, and an inability to meet evolving customer expectations. Operational risks. These are risks associated with the functioning of AI systems themselves. This includes system failures or malfunctions which could disrupt business operations. There's the risk of over-reliance on AI, where humans become too dependent on AI systems without adequate understanding or oversight. A major challenge is the lack of explainability in some black box AI models, making it difficult to understand why a decision was made, which is problematic if the decision is wrong or biased. And of course, bias embedded in AI models, often stemming from biased data or flawed algorithms, can lead to unfair or discriminatory outcomes, damaging operations and reputation. Financial risks. AI initiatives can involve high upfront costs for development, talent, and infrastructure with an uncertain return on investment, or ROI, especially in the early stages. AI systems can also be targets for new types of fraud. And if an AI system causes harm or makes costly errors, there can be significant liability implications. Reputational and ethical risks. These are incredibly important. Poorly designed or unethical AI can lead to severe public backlash and a significant loss of trust from customers and the public. Misleading marketing about AI capabilities, AI washing, can also damage reputation when systems fail to deliver on inflated promises. Legal and compliance risks. As AI regulations like the EU AI Act become more prevalent, there's increasing regulatory scrutiny. Errors made by AI systems in areas like contract generation or legal analysis can have serious consequences. And as mentioned, violations of ethical principles can also translate into legal and compliance breaches. Cybersecurity and data risks. AI systems, especially those trained on large data sets, can be vulnerable to data breaches. They also introduce new types of adversarial attacks where malicious actors try to fool or manipulate AI models, e.g., by feeding them slightly altered images that cause misclassification. And the use of personal data in AI systems raises significant privacy violations concerns if not handled correctly. To address these, businesses need an AI business risk impact assessment. This involves systematically identifying the most significant AI-related risks that could affect the organization, evaluating their potential impact on business objectives, financial, operational, reputational, etc., and documenting any risks that are not adequately addressed by current controls. This naturally leads to the critical topic of AI governance for business. Strong governance is the framework that enables an organization to harness AI's benefits while managing its risks. A cornerstone of AI governance is leadership commitment. Effective AI governance starts at the top. There must be clear executive sponsorship to champion the AI strategy, drive the establishment of robust governance structures, and foster an ethical culture around AI use. This commitment should translate into a formal AI governance framework, which often includes clear lines of accountability. A common model for these lines of defense is first line operational teams. These are the business units and AI development teams who own and manage AI risks as part of their day-to-day responsibilities. Second line, support and monitoring functions. These include departments like risk management, compliance, legal, and information security. They provide oversight, expertise, and challenge to the first line, helping to set policies and monitor adherence. Third line, internal audit. This function provides independent assurance to senior management and the board that AI risks are being managed effectively and that governance processes are working as intended. This is where professionals with credentials like the AAIA play a vital role. Fourth line, executive management. Senior leadership is ultimately responsible for the organization's AI strategy, risk appetite, and the effectiveness of the governance framework. Fifth line, board oversight. The board of directors has the ultimate oversight responsibility, ensuring that management has appropriate AI governance structures in place and is managing AI-related risks in line with the organization's strategic objectives and ethical commitments. A key component of this framework is a comprehensive AI policy. Organizations need to establish, clearly communicate, and regularly review a dedicated AI policy. This policy should be aligned with the overall business objectives and explicitly address ethical principles. Furthermore, existing organizational policies, e.g., data privacy, cybersecurity, HR policies, often need to be updated to address the unique risks and implications introduced by AI. Stakeholder management and business relationships are also crucial in the context of AI. An AI stakeholder model helps identify all the key parties involved or affected by AI initiatives. This typically includes internal stakeholders, the AI reporting group, which might consist of the board, senior management, and specific AI governance committees, the AI project teams, developers, data scientists, project managers, and other internal departments. External stakeholders, suppliers of data, models, infrastructure, partners collaborating on AI development or deployment, and critically, clients and users of the AI systems. Managing relationships with third parties and customers requires special attention. Organizations must diligently monitor third-party risks, especially if relying on external vendors for AI components or data. This includes due diligence, contractual safeguards, and ongoing monitoring. Responsibilities for AI systems, especially when multiple parties are involved, must be clearly allocated. Users of AI systems should be provided with clear and understandable information about how the AI works, its capabilities, and its limitations. Mechanisms for feedback from users and customers should be established to identify issues or areas for improvement. Organizations should take steps to ensure their AI systems are used as intended and to mitigate potential misuse. When it comes to AI suppliers, organizations need to think about a responsible supply chain. This includes suppliers involved in data/model development, those providing data sets, pre-trained models, or custom AI development services. Infrastructure, providers of cloud computing, hardware, or AI platforms. Governance, compliance, consultants or tool providers specializing in AI ethics, risk management, and regulatory compliance. Security, privacy, vendors offering solutions to protect AI systems and the data they use. Finally, effective AI adoption requires careful resource management for AI. This starts with budget and investment. AI is not cheap. Organizations need to ensure adequate funding is allocated for research and development (R&D), for the actual deployment and integration of AI systems, and for ongoing support, maintenance, and retraining. It's also essential to create AI resources documentation. This involves identifying and formally documenting all the critical resources needed for the organization's AI initiatives. This documentation should cover human expertise, the skills and roles required, e.g., data scientists, machine learning engineers, AI ethicists, domain experts, data engineers, AI auditors, computational infrastructure, the necessary hardware like GPUs, software platforms, and cloud services. Data sources, clear documentation of the data used for training and operating AI systems, including its origin, lineage, quality, and governance. Software tools, the specific AI development tools, libraries, and platforms being used. Financial investments, a clear record of the budget allocated and spent on AI projects. By carefully considering these business aspects, the opportunities, the strategic planning required, the myriad risks, the governance structures, stakeholder relationships, and resource management, organizations can navigate the complex world of AI much more effectively and responsibly. And for us, as current or aspiring AI auditors, understanding this business context is just as important as understanding the technology itself. It allows us to assess whether AI is not only technically sound, but also strategically aligned, well-governed, and ethically managed. This comprehensive overview of AI models, considerations, and requirements provides the essential foundation we need as we delve deeper into the specifics of AI auditing and the AAIA credential. Thank you for watching, and as always, continue learning, stay curious, and we'll see you next video.